Um, I think, as I mentioned last week, the exam we've decided not to do in the testing center this week, but rather I'll give you a copy of the exam on Monday next week, and then you'll have till Thursday to sort of work on it, and then you'll come and for a half hour we'll talk about your answers. And more instructions will be forthcoming, but that's sort of how we're going to do things. Any questions about that? No? Okay. Um, I am going to be out of town at the Rocky Mountain regional meeting of the American Chemical Society on Wednesday through Friday, so we won't have class those days. Um, I am willing to post replacement lectures online if you want, but I also imagine that at this time of year you're okay with not having class. So, okay. Um, we'll just we'll just do that. All right. So we're going to talk about stereochemistry today, and I think we probably will only spend today on stereochemistry. There's a couple of issues that we want to cover perhaps in a little bit more depth than you have in your introductory OChem classes, but it won't take us too long. And at the end, if we have time, we'll talk about why chiral compounds rotate plane polarized light in the first place. But before we get into this discussion of stereochemistry, we need just a bit of review on symmetry and symmetry operations. Symmetry is really important for stereochemistry. It's how we decide whether groups are equivalent or not. And in the case of symmetry, it also matters. Time scale also matters. An example of this is if you look at this compound, which is chiral, it has something that's called C2 symmetry, which is if I put an axis right here, coming out of the page and going into the page, but bisecting that bond between carbons 2 and carbon 3. And then if I rotate 180 degrees, I get the exact same thing. That's called an axis of symmetry. And because you rotate 180 degrees, that's called a C2 axis of symmetry. You get that by taking the angle of rotation and dividing 360 by that angle. And then that's your fold rotational symmetry. But of course, we can see this axis of symmetry in this conformation of the molecule. It's a little bit more difficult to see perhaps in this conformation. So, do you see how these are the same thing? Yeah. So we're going to make the assumption that it turns out you can draw a C2 axis in this conformation too. I'll just draw it here. It's this line in the plane of the page, and then if you rotate 180 degrees, you exchange places of those OH groups. But we're going to make the statement that in general, provided that conformations of a molecule can exchange fast enough on the time scale of our observations, that if a molecule has an element of symmetry in one conformation, it will have that element of symmetry permanently, right? Sometimes this breaks down, and I'll show you some situations in which it does. But this is the idea that if you can find an element of symmetry in one conformation, it applies to the molecule in all conformations, is an important one, and it's one that I use to trick unsuspecting undergraduate students in 351. I'll give them a molecule that looks like this, and I'll say, is it chiral or is it not chiral? And they'll look at that and they'll draw the mirror image, and they'll think, oh, it looks like those are stereocenters, therefore it must be chiral. But in reality, it's got a mirror plane of symmetry right here, and so the molecule's achiral no matter which conformation you draw it in. Okay. Now that's not going to be true if rotation around a carbon-carbon bond is restricted. In general, rotation around carbon-carbon single bonds is fast, but there are some cases where it's slower, and I'll give you some examples of that a little bit later. Okay, so a C2 axis of symmetry tells you that, yeah, when you rotate by 360 degrees divided by 2 or 180 degrees, you get the same thing, and it leaves the object unchanged. This is called a proper rotation. And we're just using that to contrast with what's called an improper rotation, which I don't know really why they call it improper. It's not like it's immoral or anything, but it involves both a rotation and a reflection through a plane. So improper rotations are rotations about an axis that you define by 360 degrees divided by whatever that n term is, 1, 2, 3, and so on, plus a reflection across a mirror plane that is perpendicular to the axis. Josh, I know that Professor Stowers has been doing this. Have I defined that correctly? Did I miss anything there? Perpendicular to the rotation axis. Okay, what do we mean by that? So let me give you an example of an S2 symmetry operation. And actually, this is going to be that compound I showed you above, which I've already told you is achiral. So we're going to define a rotational axis here. It's perpendicular to the plane of the page, and if we spin 180 degrees, that's going to give us what we've drawn here. We're just literally spinning the molecule around. And then, and remember, our axis is coming out of the page and going into the page. So our reflection, so this was the rotate part of the operation, then we need to reflect through a mirror plane that is perpendicular to our axis, and that would just be the page. So if we allow the page to be our mirror plane, this OH group, which was back, will now be up, and this OH group, which was up, will now be back. And we now have our molecule again. So this molecule has S2 symmetry. When a molecule has S2 symmetry, or any improper rotation symmetry, it is achiral. Okay, so any molecule with SN symmetry is achiral or not chiral. I always struggle with that because I'm afraid when I say this is an achiral molecule, people are going to hear that I said it's a chiral molecule. So I have to be very careful. It is a not chiral, achiral molecule because it's the same as its mirror image, right? Because rotation around an axis doesn't really change the connectivity, and then you reflect through a mirror and it's the same as its mirror image. So one of the ways we can define chiral molecules is by saying they lack any improper rotation axes. The simplest improper rotation is just S1, which means rotate 360 degrees and then reflect. That's basically just mirror plane symmetry. Okay. And we're going to use these symmetry operations to determine in molecules whether groups are identical or not. And this can be useful in evaluating reactivity of molecules. And it can also be really, really useful in NMR interpretation. So deciding whether groups are same or different can be challenging. We're going to talk about 3 different kinds of groups that are related by symmetry to each other. So the first kind of groups are called homotopic groups. And these are interconvertible by a proper rotation, by a C, whatever n is, axis of symmetry. And homotopic groups are always equivalent, even in chiral environments. So an example of this would be propane, HA and HB. Those are exchangeable by a C2 axis of symmetry that I've drawn there, rotate 180 degrees. HA is always equal to HB, even if you put propane in a chiral environment, they're going to be the same. All right. Second, and there's other, I guess, examples, sorry. So, this acetal, you've got 2 different methyl groups and 2 phenyl groups. The axis of symmetry is again in the plane of the page. That means that these 2 phenyl groups are equivalent to each other, and these 2 methyl groups are equivalent to each other always and forever, even in chiral environments. We can also use the term homotopic to describe faces of planar molecules. So as an example, if I look at this ketone, acetone, and it's lying within this plane that I'm drawing, you've got the top face and the bottom face of the molecule. And if I rotate around this C2 axis by 180 degrees, face A becomes face B, they're exactly the same. And so we would say this ketone has homotopic faces. And this is important because you think about a nucleophile attacking this molecule, a nucleophile can't distinguish between homotopic faces. They're exactly the same. So there's no way to say, well, I want a nucleophile to only come in on face A versus face B. It's the same thing. Okay? And that can lead to predictions in terms of reactivity. Now, besides homotopic, you've got enantiotopic groups, and sometimes this is difficult to distinguish between homotopic groups and enantiotopic groups. Enantiotopic groups, unlike homotopic groups, enantiotopic groups are interconvertible by an improper axis of rotation, where n equals 1, 2, 3, and so on. They are equivalent mostly unless you're in a chiral environment. I guess I should, instead of unless, the right word is except in a chiral environment. Okay, so what are some examples of enantiotopic protons? HA and HB. All right, well, how are they interconvertible? they're interconvertible by a mirror plane, which is just the plane of the page. And that mirror plane is really just an S1 axis of symmetry. That is, if we put the axis right here, spin the whole molecule around by 360 degrees, and then reflect it, HA becomes HB. Alternatively, you can just think, okay, well, the S1 improper rotation is a mirror plane. So if you can find a mirror plane that exchanges the positions of HA and HB, then they are enantiotopic. This may be more straightforward to think about than I think what a lot of textbooks teach, which is you do a thought experiment and you replace one of the protons with some Z group, and then you replace the other with the Z group, and you see if they're enantiomers, and if they are, then those two groups are enantiotopic. That works too, but it's a little more clunky, and I think it confuses students because they're like, what the heck is the Z group, and why am I doing this in my brain? And the whole point is identifying whether protons are equivalent or not. So enantiotopic groups are equivalent except in a chiral environment. So what this means is if I were to have some chiral molecule that bound this molecule, imagine your hand is a receptor for this molecule, and your hand is chiral, right? And it has to bind with the methyl group in the palm and the chloro group in the fingers. There's only one way to do that. And when you do that, HB is pointing towards your palm and HA is pointing out. They're different in that case. But otherwise, outside of a chiral environment, they're exactly the same. So this is important because homotopic protons or groups can't be distinguished by chiral reagents, but enantiotopic groups can. So if you're trying to, if you find yourself in a situation where you're banging your head against the wall trying to figure out how to distinguish homotopic groups, don't bother. It can't be done. In contrast, enantiotopic groups can be distinguished. Sometimes we will call these protons that are enantiotopic, sometimes we will call them prochiral, meaning sort of before chirality. The molecule isn't chiral, but if we replaced a proton with something else, it might be. So sometimes there's some terminology that you may hear of. They'll call this the pro-R proton because if you replace this with, say, like deuterium and then assigned priority 1, 2, and 3, this would be an R. This stereocenter would have R configuration, whereas the one, if you replace the proton in the back with, say, deuterium, the stereochemical configuration would be S. So sometimes people call this a pro-S proton. And basically, enantiotopic protons or groups are sort of like any time you have two of the same atom or group attached to the same carbon in a molecule that's not chiral, but where if you did something to that carbon, it could be chiral. So this is a case where the two chloros are enantiotopic. As before, we saw homotopic faces with ketones. We can get enantiotopic faces with some sp2 hybridized compounds. So let's do a ketone where the two groups attached to the sp3 hybridized carbon are not the same. And you have as before, you have the top face, face A, and the bottom face, face B. And they're mirror images of each other. If we let's look at the view if we approach the molecule from face A, the methyl groups on our right, the ethyl groups on our left. Excuse me. Face B, on the other hand, if we looked from underneath this plane, this is what we would see. I'm not getting emotional again. I'm just still recovering. They're mirror images of each other, okay? And they're identical except in a chiral environment. Same argument we used before for the enantiotopic groups. If your hand is a receptor and you have to bind the ketone and your fingers always need to be, and you have to bind it with your left hand, your fingers always need to be in the methyl group, your palm always needs to be on the ethyl group, you can tell one face from another with this reagent. And so these are called enantiotopic faces, and there's a stereochemical way to distinguish them. What you do is you assign priority to the three groups attached to the sp3 hybridized carbon. Oxygen's 1, the ethyl group carbon is 2, the methyl group is 3. That's counterclockwise, going from 1 to 2 to 3, and so we call that the psi face, S-I. I didn't make this stuff up, I'm sorry. So this is the psi face of the ketone, and 1, 2, 3 clockwise. This is called the ray face. And why do we do this? Well, imagine if you were to try to reduce this ketone by delivering, a proton from the top, delivering a hydride from the top, what would the stereochemistry be? Well, if we delivered a proton from the top, that proton would be pointing out at us, the oxygen would be pointing away, and we would assign stereochemistry, and it would be S. In contrast, if we were to add a hydride from the ray face up from the below, then we would assign stereochemistry, and it would be R. I'm not sure. You can sort of see that? Psi face and ray face. Well, let me... So if we were to reduce the ketone with, say, I don't know, lithium aluminum hydride from the psi face, that would give us the following molecule. On the other hand, if we did it from the ray face, we would get this one. Those two are enantiomers of each other, and if we assigned stereochemistry, 1, 2, 3, counterclockwise rotation, this stereocenter would be S, and this one would be R. So that's why these two faces are different. Yeah?
And those two would show up 50-50, right?
They would show up 50-50 unless you're in a chiral environment. Right? So if you had a chiral reducing reagent, you could, in principle, select for one face over the other face. Because remember, enantiotopic groups or enantiotopic faces are only the same except in a chiral environment. Our analogy would be, if your left hand is the receptor, and again, your fingers always need to be on the methyl group and your palm always needs to be on the ethyl group, cupping this molecule from underneath, you've blocked one of the faces. So you can select one from the other. Yeah. Other questions on that? So there's a whole host of reactions in organic chemistry that I don't really know very well, but they involve what's called asymmetric induction. That is, can we get a stereocenter by distinguishing between two enantiotopic groups and using a chiral reagent to do so. And in many cases, this is done using catalysis, where you have a small amount of a chiral reagent that generates a lot more of one enantiomer than another in a product. Okay, so that's enantiotopic, and I did not really understand this. I think when they tried to teach it to me in 351 and 352, I don't think I understood it when I took the undergrad lab here. I don't think I even understood it in grad school. So this is the way the Anslin and Doherty text explains this is actually the best I've ever sort of didn't click until this. So it can be useful. Anything else we need to say about that? Okay, let's go on to the one that I think a lot of people, a lot of your undergrad students are going to struggle with, which is diastereotopic groups. And again, the way that this is typically taught is, well, you do the thought experiment, you trade one proton for a Z group and then the other, and then you see if they're diastereomers, and if they are, they're diastereotopic. Okay, but another way of saying this is diastereotopic groups cannot be interconverted by any symmetry operation and are therefore always different. So what are some examples of that? Well, the classic example of diastereotopic protons is a CH2 group in a chiral molecule. There's no mirror plane that will interconvert A and B, because the mirror plane would also switch the position of this OH group. And so worlds without and proton A and proton B are not the same. They are diastereotopic. We can do this with sp2 hybridized carbons as well. So if you have a carbonyl carbon and it's in a molecule where there is a stereocenter, so we're sort of looking down this carbon-carbon bond. There's a stereocenter here. Then there are two different faces of the carbonyl compound, face A and face B, and they are non-equivalent. Okay? To demonstrate that this is the case, let's imagine approaching from face A. I guess I didn't just draw a straight line there. So we've got, if we were to approach from face A, the methyl group would be on our right. And I think as we've drawn it, the chloro group would be away from us. Okay? And if I were to approach from face B, the chloro group is coming towards me. Right? Those are two different situations. And frankly, it doesn't matter how much I rotate around this carbon-carbon bond. I can never get exactly the same situation, right? You could say, well, okay, fine. What if you rotate here so that the chloro group is up? Okay, we can do that. That sounds... But then we'd be in that situation. It's not the same. The methyl group's in a different spot. So when you have a stereocenter in a molecule, the two sides of an sp2 hybridized carbon are different. They are diastereotopic faces. And so this might be a case where you could do, where you might have some, there could be some preference for reactivity from the face A versus face B. And you wouldn't need a chiral reagent to have that reactivity. They're different, and so the rates of reaction from either face could be different. This is another popular method of using stereochemistry in one part of the molecule to get more stereochemistry in another part of the molecule. If by having a stereocenter here, you can influence future stereochemistry there, then that can be an efficient way to have things go. All right. Anything else on that? Let's talk about reactivity consequences. This is kind of boring. It's sort of a rehash of what we've done. I guess it's a review. Remember, this ketone has homotopic faces, which means that if we were to do a reaction, let's just say it's lithium aluminum hydride reduction, the products we get from reacting with the top face versus the bottom face are identical. So here's top face, here's bottom face. Exactly the same. So that's important because you know if the two faces of a molecule are homotopic, you don't need to worry about whether or not you have stereoisomers as products. You don't. In the case of a molecule being enantiotopic, which I think we talked about, enantiotopic faces, we're going to get two products, right? We're going to get this stereoisomer and this stereoisomer, and we have to get them in a 50-50 ratio unless we're using a chiral reagent. So a molecule with enantiotopic faces will, if you deliver a reagent from one face versus the other, you'll get different enantiomers. And then our final example was the molecule with diastereotopic faces. If we reduce from above versus below, we actually get diastereomers rather than enantiomers because that other stereocenter is not affected by the reaction. Oops. Okay. When's this likely to come up in your future research careers? If you're going to do a lot of synthesis, you'll be thinking about this kind of thing from a design standpoint. But even if you're just doing routine synthesis of known molecules for other things, which is sometimes what we do in my lab, you're going to encounter diastereotopic protons. Anytime you have a molecule that's chiral and you got a CH2 group, you should expect to see two different NMR signals. Now, just because two groups are diastereotopic and are technically different doesn't mean they have to have dramatically different chemical shifts. And so sometimes, depending on how close a CH2 group is to a stereocenter, the difference between two diastereotopic protons may be small enough so as to be negligible, but that's sort of what we're talking about. All right, so we talked about how being able to interchange groups by symmetry axes, and I gave you the idea that if a molecule had an element of symmetry in one conformation, it counted as though it were present in all conformations. And this is where the issue of time scale becomes important. Because whether rotation and interchange of conformations is slow or fast on the time scale of whatever observation we're making can influence our conclusions. As an example, we already talked about how in 2-butanol, the CH2 groups are diastereotopic. And we've typically said, or we didn't actually say, but we just sort of assumed that these methyl protons are identical because we assume that rotation between rotation about the bond between carbons 1 and 2 is fast. But if it weren't, if we could slow it down, then suddenly those protons would be different because we could no longer interchange their positions by rotation around that carbon-carbon bond. If we slow down rotation, then they could be different. So even the conclusion that methyl protons are always identical only applies to molecules where rotation around a carbon-carbon bond is fast, which happens to be most of them. But here's a sort of fun, a lot of physical organic chemistry is these extreme examples that really push the principles and force you to deal with the way things really are rather than the simplified way that you think they are. So here is one of these sort of fun examples. It's not useful for anything, but it demonstrates the principle. So this is a really wacky bicyclic compound. You've got a phenyl group up here. You have another one here. And for fun, there are CH3 groups. And then there's another phenyl group here. I'm getting tired already. I'm not sure how they made this. I'm even less sure why they bothered. And then coming out at you is a methyl group. Okay, and sorry. And you might imagine if you could build a model that there would be some amount of steric hindrance by those groups on the phenyl rings that could prevent those protons from rotating quite as freely. I mean, ideally, the way this would be, it would be really awesome if this worked so that they were different at room temperature. But these folks had to cool it down to minus 90 degrees Celsius, and then they were different. So at 90 degrees Celsius, you actually see 3 NMR signals for the methyl group, indicating that those methyl groups, those methyl protons are now diastereotopic. They're different from each other. Why is this cool? Well, remember the barrier to rotation around a carbon-carbon bond is usually in the 5 to 10, or, I mean, depending on whether you're dealing with ethane or butane, it can be anywhere from 2 to 3 or more kilocalories per mole. And at that kind of barrier, you're not going to freeze out individual conformations, even at really, really low temperatures. So the fact that they could do so at a temperature you can get to basically if you have dry ice and acetone is pretty impressive. Okay, so if you can restrict rotation around carbon-carbon bonds, then then protons in a methyl group can be different. There's also examples of enantiomers that can exist and be separated because rotation around a carbon-carbon bond is slow. We may have dealt with this a little bit before when you were doing calculations on conformations of butane, and I told you to only worry about the unique conformations. And some of you would have noticed that there are 2 equivalent Gauche conformations of butane. And they actually look like they're enantiomers, right? The mirror plane would be right here. Everything on the left is a reflection of what's on the right. We called this one Gauche plus because going from the front proton or front methyl group to the back proton is counterclockwise. We called this Gauche minus. Sorry, that's clockwise. And we called this Gauche minus because going from the methyl group in the front to the one in the back is counterclockwise. I'm not sure if I've got that sign convention right, but anyway, they were different. But they were, we don't consider them enantiomers because they rapidly interconvert at all temperatures that we're interested in. We'll just say room temperature and so on. And actually, if you looked at some of the barriers that you calculated, going through you would think these two conformations would have to interchange via a methyl-methyl eclipse, but that barrier is really high, and actually much lower would be to go the other direction through the anti-conformation, through those methyl proton eclipses to get to the other Gauche. So the barrier here isn't high enough so that we can isolate two enantiomers of butane, which I think makes the world a simpler place. But there are molecules that are similar to this where the Gauche plus and the Gauche minus conformations are different. So a classic example is something called Binaphthal, or I think is often just called binol. This is two naphthalene groups attached to each other via a carbon-carbon bond. But this thing has all kinds of conformational problems because if it was planar, you'd have groups bumping into each other. And I'm sorry, there's also, to make matters worse, there's also an OH group there and an OH group there, and those would bump into each other. So this molecule actually exists, has two possible enantiomeric forms. One is to have the ring on the left twist towards us, such that the methyl group and the top of the benzene ring are coming out towards us, whereas the bottom of the bottom of the naphthalene ring is pointing down into the page, and then similarly we would have this OH group pointing away from us. These two carbon-carbon bonds would sort of be backing away from us, and these would be coming out toward us. And then you would have the other enantiomer where it would be the other way. So let's just draw that one quickly. And it can be difficult to visualize why these two, oh my goodness, why these two are enantiomers of each other unless you look at a space-filling model. So we'll do that in just a second. Those two conformations of this molecule are enantiomers because rotation around that carbon-carbon bond is slow enough that you can separate these two molecules and use them. In fact, these are often used as chiral ligands for various catalysis, transition metal catalyzed types of reactions. So let's go look at one of these binols that I drew, and you can see that they're not even kind of planar, right? And so we're looking at them. And so that's really hard to draw. I'm sorry. Excuse me. That's really hard to draw, that they're sort of at 90-degree angle with respect to each other. The drawing that I did over here in Notability really doesn't capture that, but that's sort of what it looks like. Now, to give you a sense for why these two groups would have a hard time, why these two naphthalene rings would have a hard time sliding past each other, let's look space filling. No way, right? Those protons on the hydroxyl groups have sort of locked things in. And I'm not sure what the barrier to rotation for this molecule is. It's known. I also don't really know how you get one from the other, but presumably having made a 50-50 mixture of both, you can separate them on some kind of chiral column. So those are practical details. Now, this is bizarre in some ways because this is a chiral molecule without any stereocenters, right? I can't point to a tetracoordinate carbon that has 4 different things on there. I can't identify a stereocenter. So we have to have a different way of talking about chiral molecules that are chiral because of slow rotation around a carbon-carbon bond. These two are enantiomers, and that is a correct term, but the ability of, well, another word we sometimes use, you will hear people use to describe molecules where enantiomers could be interconverted by rotation around a carbon-carbon bond, but rotation is slow. They call those Atrop Isomers. So you'll occasionally hear people use that word. Enantiomers is just fine. But how would we distinguish one of these from the other? So you first have to identify the bond where if you rotated around it, you would interchange the two enantiomers. So that's this one, right? Then we're going to do, you're going to love this, Newman projection, where we will cite our jaundiced Sith eyes down this carbon-carbon bond. And let's see what we would see. So let's imagine we're looking down the molecule in the plane of this ring. And we'll actually do that here in the stick setting. Let me make sure. Yep. Not going to want to rotate for us. So as we look down that axis, we could draw a line here in the front for the front group and a line here in the back for the back group. And the two sides are different, right? This side has an OH group and this side has a benzene ring. This side has an OH group and this side has a benzene ring. So what we would do is, let's see here, looking down this bond, the OH group would be on our left and the ring would be on our right. Then in the back, the OH group would be pointing down and the ring would be pointing up. We identify the highest priority group in the front, which is the OH group. And we identify the highest priority group in the back, which is the OH group. Then we draw an arrow from priority group in the front to the one in the back. That is counterclockwise rotation. So the designation for that is M. There are two, these are called Atrop isomers or helical isomers, and the terms for helical chirality instead of R and S are M and P. Nevertheless, Binaphthal will still be sold as R versus S naphthal. I don't know what convention they're using there, so go figure. Similarly, if we were to look down this carbon-carbon bond, what would we see? Well, we'd see the OH group here on our left, the ring on our right. In the back, OH group would be pointing up and the ring would be pointing down. That's clockwise rotation, and so that would be the P isomer. Okay, so you can assign. This is an example of what's called helical chirality, and you can assign stereoisomer designations with M and P. Most people don't know how to do that. I didn't know how to do it until like this morning, so for what it's worth, but it's good to be aware of. And it's good to at least know when people use those terms what they're talking about. All right, that's enough for today. We'll see you, I guess.